In this video, we're going to look at calculating the Fourier coefficients of a Fourier series where we're given a function with a general time period t. So rather than having a time period that's in terms of pi, as we probably often started off with, in our example, we're going to look at a time period of t, capital T. So here, the method is pretty much the same. You just need to use the formulae that are given here. So on the left-hand side, you've got the general formula of the Fourier series with time period t, and the way to calculate the coefficients, the an and the bn, are given by the formulae on the right-hand side. So we're going to do an example. Our example will be to calculate the e.g. find the coefficients of the Fourier series for our function is going to be defined by ft is the modulus of t. And we're going to define this for t between -2 and 2. And to make it periodic, we're going to say that ft plus 4 is equal to ft. So this means this is a ft plus 4 equals ft means this is a function with period 4. So we are going to, this capital T, our period is going to be 4. It's always useful in these examples to actually sketch our function. So the modulus function is the function that, well, let's define the modulus function. Mod t is equal to t if t is a positive number, and is equal to minus t if t is a negative number. So the modulus function is always a positive number. We can sketch this function between 0 and 2, then t is a positive number, so mod t is just equal to t. So we have between 0 and 2, mod t is just equal to t, and between 0 and minus 2, t is a negative number, so mod t is equal to the negative of t. So this is our mod function defined on between -2 and 2, and by our ft plus 4 equals ft, this is going to be a periodic function with period 4, so it's just going to repeat. So this is what our function is going to look like. Okay, hopefully that makes sense. It's always useful to sketch these functions whenever you're doing a Fourier series question. You can see from this picture that this is an even function. How do we know it's an even function? Well, even functions are symmetric in the y-axis, and this one is in y-axis. The idea is that ft is equal to f minus t. That's what an even function means. And thankfully, if we have an even function, it makes calculating our Fourier coefficients really easy, because the sine coefficients, the bn's, are going to be 0 for an even function. If we had an odd function, the cos coefficients, the an's, would be 0, but for an even function, our bn's are equal to 0 for all n. You could calculate the bn's if you want, just to check, but save yourself some time, note it's even, and then you don't have to calculate the bn's. So we're only going to need to calculate the an's. So let's just copy this formula down, just to make it easy to refer to. So here's our formula. So an is equal to 2 over t, well remember t was 4, so it's 2 over 4, and it's the integral from minus t over 2 to t over 2, so it's integral from minus 2 to 2 of ft, well remember ft is mod t, the integral of mod t cos 2n pi t over capital T, which is our period, which is 4. So here's our formula to calculate the ANs. We can substitute, we can change this slightly because it's difficult to integrate with mod functions, but thankfully we've redefined the mod function. Mod t is equal to t if t is greater than 0, and it's minus t if it's less than 0, so we can split this integral up into two pieces. 2 over 4 is 1 over 2, and we can split the integral up into a 0 to 2 piece. 0 to 2 is where mod t equals t, cos 2n pi over t. 2n pi t over 4 is just n pi t over 2. So that's our 0 to t piece, and we also have the other piece which is from minus 2 to 0, and in that region mod t is just equal to minus t. Again, we have cos n pi t over 2 dt. So this is the integrals we're going to have to work out to find our ANs. Now, if you're a bit clever, you can see that these two integrals are actually exactly the same. By sort of symmetry, they're going to give the same answer. One goes from 0 to 2, and the other goes from minus 2 to 0. And cos is an even function, so the one with the minus t and the negative values of t is going to be exactly the same as the one with the positive t and the positive values of t. So actually these two integrals are exactly the same. So this is just the same as one lot, or two halves make one lot. So this is the same as one lot of t cos n pi t over 2 dt. Okay, now this is t cos n pi t over 2. To integrate this, we're going to integrate by parts. So we're going to define u equals t and dv by dt equals cos n pi t over 2. Then du by dt is equal to 1, and v is equal to 2 over n pi sine n pi t over 2. Okay, so we do this integral, we get the uv is 2t over n pi sine n pi t over 2, and this is between 0 and 2, and then we have to subtract the integral of v du by dt. Well, thankfully du by dt is 1, so this is just v, this is 2 over n pi sine n pi t over 2 dt between 0 and 2. Now, thankfully, if we know anything about sine, we'll see that sine, if we substitute t equals 2 or t equals 0 into the sine n pi t over 2, these are both equal to 0. This whole first term is just 0, so we get equals minus, now integrating sine n 2 over n pi, this is 2 over n pi, the integral of sine n pi t over 2 is minus cos It's actually minus 2 over n pi cos n pi t over 2, which we multiply this, we get 2 over n pi times 2 over n pi. This is 4 over n squared pi squared. We substitute in our limits, we get cos, when t equals 2, we get cos n pi, and when t equals 0, we get 1. Take away 1. And a useful result whenever you're doing Fourier series is that cos n pi is equal to minus 1 to the n. So this just comes to 4 over n squared pi squared minus 1 to the n minus 1. And minus 1 to the n is equal to 1 if n equals 0, and it's equal to minus 1 if n equals if n is equal to 1 if n is an even number, and it's equal to minus 1 if n is an odd number. So this whole thing comes to 0 if n is even, or 4 over n squared pi squared times minus 1 is minus 2, so it's minus 8 over n squared pi squared if n is odd. This sort of idea is quite common in Fourier series. You'll have sort of different coefficients depending on whether n is an odd or an even number. So in this case, I think you get, if n is even, then we get 0, and if n is odd, we get minus 8 over n squared pi squared. When we say n is even, this is sort of n is greater than or equal to 2. So you sometimes have to consider the n equals 0 case separately, because the n equals 0 case, so a0 is equal to, in this case it's 2 over t, so 2 over 4 times the integral of ft dt, between, in our case, between 0 and 2, between minus 2 and 2, which is a half the integral between 0 and 2 of t dt plus the integral from minus 2 to 0 of minus t dt. Again, splitting as before to deal with the mod t idea, which is a half t squared over 2 between 0 and 2 minus t squared over 2 between minus 2 and 0, which is this first one, it's a half. T squared is 4 over 2, so we get 2 minus 0 is the first term, minus 0 minus 2. So just need to be quite careful here, but this is a half of 4, which is 2. So a0 equals 2, which means that, remember, if we go back to the top, our function has this a0 over 2 term. So our actual function has our a0 over 2 term. So a0 over 2 is equal to 2 over 2, which is equal to 1. And this should be the average y value of our function. And indeed, if we think about our graph, the average y value, because of the symmetry, is indeed 1. So it looks like we've got this right. Obviously, you could just, if the graph is really obvious, you could write down a0 over 2 equals 1 straight away. You wouldn't actually have to do this long a0 calculation. Okay, so now we have to go back to actually writing our Fourier series. So ft equals, well, it's a0 over 2 is 1, and then plus, and we're going to have this sum from n equals 1 to infinite of an cos 2n pi t over 4, it's capital T, plus the, well, we know the bn's are 0, so we don't need to, we can just stop there. So this is our Fourier series. We now just have to substitute in the values of an. Well, remember, an was 0 if n was even, and minus 8 over n squared pi squared if n is odd. So we don't even need to put in the even ones, we just have to put in the odd ones because the even ones were 0. So this is 1, it was minus, remind myself, it was 8 over n squared pi squared. 8 over n squared pi squared cos 2n pi t over 4 simplifies to just n pi t over 2. And remember, this is only for n is odd. So it's n equals 1 to infinite n odd, because the even terms were all 0. We can simplify this a little bit. Let's bring the constant 8 over pi squared outside. This is 1 minus 8 over pi squared, sum from n equals 1 to infinite n odd, 1 over n squared cos n pi t over 2. Okay. Hopefully I haven't made any mistakes there. It's quite easy to make mistakes in this thing. Now, because n's an odd number, we can rewrite that as, so let n equal 2k plus 1. So an odd number n can be written as 2k plus 1. So this is the same as a 1 minus the sum from 8 over pi squared. And now the sum, rather than summing over n, we're just going to sum over k. And to get n equals 1, we want k equals 0. So our sum is now going to go from k equals 0 to infinite of, and then rather than n, we're going to write 2k plus 1. So we're going to get 1 over 2k plus 1 squared cos, again we're going to replace n with 2k plus 1, 2k plus 1 pi t over 2. So this converting n's into 2k plus 1 isn't strictly necessary, but it makes it a little bit clearer on your summation, because now you're not having to restrict your summation only to odd values. We now allow the whole summation from 0 to infinite, and we can work out the first few terms. So if we try k equals 1, we get sort of 8 over pi squared. So k equals 1 gives us 1 over, so k equals 0 is our first term. So we get 1 over 1 and then we get cos, when k equals 0, we get cos pi t over 2. Now if we do k equals 1, we get 1 over 3 squared, when k equals 1, so it's 1 over 9. We need to keep that 8 over pi squared term. So we get 8 over 9 pi squared cos 3 pi t over 2. And then when k equals 2, we get n equals 5, so we get minus 8 over 25 pi squared cos 5 pi t over 2. And so now the pattern's sort of quite clear. We can see what's happening on. These are the first few terms of this Fourier series. We've also got the general term, which was above. They can be quite long, quite involved calculating these Fourier coefficients. Hopefully this example helps you see sort of how to approach a question like this.